Hello everyone, welcome to my YouTube channel. Today we're going to talk about this amazing paper called Implicit Warping for Animation using Animate sets. This paper has been published by NVIDIA and they were able to achieve remarkable results. So without any further ado, let's hop into it. Okay, now we need to learn what is the goal of this paper. The main goal and contribution of this paper is to be able to generate a video using a different source image. However, they are using the motion from other video itself. As you can see here, this is an example for faces where the source image is from a different identity and the driven video is from a completely different person. And the model is trying to use the driven video and capture its motion and try to warp it over this new face that it has. And as you can see, the results from left to right are from the main driven video itself, the first order motion model, then the vid to vid, which was also created by NVIDIA, and also the last but not least is the main video from the original paper itself. And it's not just about the faces, it's also for pose and gesture as well, which, as you can see, the source image and the driven video are from, though they are both from the same identity, but they're generated from a single or multiple images. And the results are from left to right is the driven video and their model, but they just used one single source image. And the second one is the first, and the third one is the first order motion model, and the last one is their own results. We can also take a look at previous models and papers who have been published in the similar domain. First one is the first order motion model, which was trained on face images. The AAPCA, which was mainly trained on pose and gesture images. And the last but not least, the vid to vid, which was trained on face images. But there's one thing they all have in common, is that they usually use one single image for the source image and identity, which has some issues, and these sort of models typically perform weak around the areas and regions where there isn't enough information. And here is a simple example. You can see the video over here. If you notice these two videos behind the scene, behind the person, there is some ambiguity and the model is not able to recognize and generate the information that it was supposed to. And the reason is simple, because there wasn't any information in the source image regarding that region. As I mentioned, one of the issues with using a single image as a source image, the model is not going to be able to recover some parts of the video that has sort of ambiguity. And one of the ways that they could solve this problem potentially is to use multiple frames for the source image. However, that approach also has some downsides. For example, if you try to use averaging over the results of using multiple source images, you're going to get a very blurry output. However, if you try to use the most appropriate and the best fit one, you will see some flickery over the output, which in these videos you can notice that one is actually using blurring and the other one is actually using selecting the most appropriate one. And the third one from the left, you can notice that there is some flickery in the output, and that is the cause of using this effect. So what they actually came up with is that they are going to train this entire model using multiple source images, but in the end-to-end way. And their approach has a few benefits. One of them is that they don't need an implicit representation for the key points in the space, so there's no need for supervision over where the exact key points should be located, which I'm going to explain more into details in the rest of the slides. And other than that, there is no need for a per source image warping, and that is also a benefit. They made a slight update towards their model, which we're going to go over the previous versions, which were more related to the vid to vid and the first order motion model. So in the first step, they were able to detect something around M key points from both the source image and a frame from the driving video. And what they did after that is that for each key point inside of the source image and the motion frame, they calculated a flow. So what they eventually got in the output was that they had M flow fields, which each one of them corresponded to the movement of each key point. and they used those motion fields and warped it over the source image, which is another representation of the source image itself, and they got a new image in the output. So what they did after that was that they concatenated all those images together and passed it through this model, which they call the motion estimator, which sort of detects which motions should actually be used, which is similar to the attention mechanism, where they have multiple frames of the image and each one of them is warped or changed in a specific way, but the model is trying to learn which ones are the most appropriate and which ones should be used. Then they are going to use that mask, and they are going to apply that mask, which kind of relates to trying to apply the attention of the importance of each key point to that specific part. And then they're going to have this final flow field, which they are then going to apply to the features that they got from another network. Okay, now we need to know what does this model do. So in the first step, it gathers the image and a bunch of unsupervised key points, and they concatenate these information all together and pass it through this network, which is an encoder that will gather some source features from the images. And there's going to be multiple images in the input, not a single one, as we mentioned, is one of the contributions of this paper. And then these results are going to be the source key point features, which are going to go into this transformable attention model. Other than that, the model also gathers the key points from the driven video. So the thing is, this time we just use the key points locations. We don't use any representation of the frame itself, and that is how they will enforce the output. Use the source information, but use the motion and the movement on the feature space, not the identity and the shape of the driven video itself. And they also have another network will get those features and like a latent representation of the image itself, as you can see on the top from the source image, and then they use all these information gathered and then use this cross model attention model, and then they work similar to a transformer model, and then they are able to extract the features that they want. I also mentioned about the fact that this model uses the key points from an image or a frame, and they use the key point as an information as well to do some tasks. So we want to go into a bit more details about this. So the model that is able to detect those key points is typically a UNet model, where on the last frame so the UNet model, typically what it does is an image-to-image translation, which the input is going to be 3 channels RGB, and the output is also going to be an image. However, in this case, when they get they get a 67 channel output, and then they use those 67 channels, and they get other information. One of them is a representation of the strength of those key points, which is technically a scalar, and another part is the key point itself, which is represented as a matrix, not like a 2D representation of X and Y. It's a grid that shows the power and magnitude for each key point. And as you can see over here, I mentioned that one of the features that we also extract is the key point strength. And the person, as you can see on the left, is talking, and the way that it's moving, based on the location that those key points are located, we're going to have different strength and magnitude for the key points. It kind of tells our model how obvious or how much we can see and notice those key points in the space. And as you can see, the key points are learned in an unsupervised manner. So we didn't decide which key point is for which part of the face. The model selects the one that has the most information in it. And as you can see over here, these are some other samples of what does the strength of this key points correspond to. So for example, these images, when the person is looking on the left side of his face or the right side of the face, the key points which do not seem to appear have less strength, so the network should pay less attention to them. And the model that you can see, the bars on here, you can notice that Some are extremely high and some are extremely low. It tells us that these feature points are recognized by the model, so it should pay a lot of attention to them. And these values are the scalars that are going to be multiplied by those key points in the space. Okay, now we go back to our first model again, and we said that there is an encoder for both the source images and the driving frames, that it passes it through the network, and we will get this feature representation that the model is going to use them to generate a new image. So we want to go into details about what they exactly are. So as we mentioned, for the source image, we were going to concatenate an image and the key point representation and pass it through the network. So in their model, they had 20 unsupervised key points, and they concatenated those matrices with the 3-channel RGB image itself and pass it through the network. The architecture of that network was a simple unit. And they also did the same thing for the frame for the driving video, but instead of they did not add the 3-channel RGB frame from the driving video. They just used the key point representation of that image and passed that through a network, which was also a unit. Okay, now we will get to the network where the input is going to be an image, and we're going to get a feature representation of that image and vice versa. So the first part is the part of the network that inputs and that has an input image, and the output we're going to have this 512 channels of feature representation, which we then use those representation as the values for our attention model, which is basically made up of a bunch of normal blocks which are similar to residual blocks. And the other part is the part where we have this latent representation and we want to generate an image. So in the end, when we have this warped feature space, which is a representation with 512 channels, it passes through a bunch of 8 residual blocks and some up blocks, and eventually we're going to have this 3-channel RGB image, which is going to be our image that we want in the output. Okay, now we get to the most important part, which is the cross attention model, which works similar to a normal transformer model which implies attention to it. So the way that it works is technically on the left side, you can see that we gather the features from the driven video and also some features from the source images, and they are both the query and the keys of this transformer model. And what they do, that they go through this scale dot product attention model, which is exactly similar to a normal transformer model, and then they create this matrix A, which is sort of like the dot product of these key features after normalization and all that. And the value of this transformer model is the feature representation from the source image that was gathered. And similar to the transformer model, they multiply those values by the product of both the keys and queries. So it will tell you the model which part of the network it should try to focus on and pay more attention to. But what is different from a normal transformer model and this model in particular is the things that are on the right side of the screen, which you can see that they also use the information from the source images and then concatenate it with the keys extracted from the previous networks, and then they multiply it by that matrix A, which was a product of both the keys and the queries, and then they pass it through this network and they concatenate it with the result with the query as well, and then they pass it through a multi-layer perceptron. And what they do in the end is that they gather the results from the previous attention model, which as I said worked similar to a normal transformer model, and then they will combine the results from that with the result of the multi-layer perceptron, and they will add it together, and that is going to be our feature representation, which they are going to use that to generate and create the new image, which we see as a normal image in the end. For their model, they use multiple data sets. For generating videos for faces, they use the talking head dataset and the Voxella 2 dataset. And for the model that was able to regenerate pose and gesture, they used the TED Talk dataset. So for their training, at first they trained their model on images size 256 by 256. And after they reached a certain point that they were getting decent results, they started to fine-tune their model on larger images, which their size was 512 by 512. And they did their training for 3.5 days over using 840 gigabyte GPUs, and they used the Atom Optimizer with a learning rate of 0.002, and the beta parameters are also mentioned on the slide, and they use several loss functions in order to train this model. The first part was the GAN loss, which with the structure of it was quite similar to the vid-to-vid model, and they also used the perceptual loss, which was the VGG19 network. And the last but not least was the equivalence loss, which was similar to their approach to the first order motion model. You can also find some references on this slide as well, which was mainly the paper itself and vid-to-vid and first order motion model. And this is about it. Thank you so much for listening until now. If you enjoyed the video, please hit the like and the subscribe button. It really helps me a lot, and I'm trying to create contents which could help you guys a lot. And if you have any suggestions for the next papers, please comment it down below, and I'll try my best to do as much as I can. So thank you so much and have a great day.